Ben Ben. Say hi to the peeps. Hello, my fellow YouTubers. This is Roy back again. Let's get right to it. So, where do we start? Just read on to this, some of my notes. And this video is not going to be on this, but the next one will. If you look here on the sphere, you got like Earth, North Pole at the top, South Pole at the bottom. But at the bottom of the South Pole, you're putting out a negative stream, and at the top, you're putting out a south stream. So what does that have to do with the price of eggs in Milwaukee? Well, as in magnetic current, Ed says if you want to eliminate loss, he says take your coil with your core and put it in a metal casing and connect one end to the casing, of the core to the casing, and you will have no loss. The most efficient, great for pulling purposes. Well, pulling is what we're talking about. Pulling electrons out of matter in the ground. So, if we talk here, we're looking at a dipole. A dipole. Two of these makes a dipole. But what really matters on a dipole is that it has a close proximity of different poles with a constant charge. So the Earth puts out the opposite stream, so it's always, that south stream is always at the North Pole, and it's chasing in both directions. So that dipole there is very, very close. And what we're going to create here on this pipe, actually with two pipes, is the same situation, a close proximity dipole. So when these strong magnets go by the pipe will fill with magnets. When the magnets are approaching, these magnets are approaching the keeper bar, which will be down in proximity, so it'll go by that bar, say, but close, the iron will react to the magnet. Therefore, it will fill up the iron with magnets. In return, when the poles change, or the snapback, the energy from the ground will flow out through the coil, which would be not this coil, but a coil similar, like, that will release out through a capacitor. And what will happen is that when this flange is north, the core of this coil will be south. And you would put a glass bottle over this section here, which, and you can't really see in this picture what he has up there, but he has these bottles hanging on the wall, and both of the bottom of the bottles are broken out. The wire is wrapped around the bottle, goes through the top, down through the bottom, out, and then there's a make or break contact down there on a loose like tin, and they make a contact. So I believe in order to create an electromagnetic field tapping through the streams of electromagnetic field of the Earth, you're first going to have to create a dipole, and you're going to use a permanent magnet to have its full dipole. And by allowing this flange and this inner core to be flopping its poles is given a pump effect to the electromagnetic stream. So in regards to the wheel, the top flange here, which is connected to this arm that Ed has out, will be changing its poles. So if you look in the picture of Ed's in his book there, you'll see that he has that pipe, he has the chains, and they're all magnetic up, so they're getting magnetized through the process and filled with electrons. So that is a lot of energy that's stored up in that metal. Up here, these are the bottles I speak about with wire around the outside. There's two of them actually, one in the front, one in the back, because there's two flanges. There's one flange that you see in the picture, and then when you go to Coral Castle, there's another one attached to this. So that means that this flange and that flange, bottom of both capacitors, is one pole. Meanwhile, the other plate of the capacitor, say the internal part of the capacitor, this would be the external, just sitting on both, would be an opposite pole, but they're dipoles and flipping their poles. So this is how this is all coming together. I hope you guys enjoy. Let's go ahead and show you something pretty cool. Let's kick on. You see this? Won't even stick. I mean, I'm getting magnetism, but this is so heavy. 1 inch and a half square stock, 6 inches long, 7 inches long. Let's click on some power. We'll put some DC current in there, and now it sticks. Now it's got some Superman strength. It's all over the place. Now let's kill the power. So the heavy one fell, of course not the other ones, because these are pretty good, because that has good magnetic strength. But this is heavy. This is heavy. This won't even stick right now. Let's turn it back on. There you go. Unplug it. We won't unplug, we'll leave it on while we talk for a second. So you get the gist of where we're going with this. Another video we'll get into three-dimensional dipole and four-dimensional dipole and so on to tetra dipole. And Mother Nature, if you stick within the 3 dimensions, you're going to stick with the rules by Mother Nature. But if you go into 4 dimensions based on using the 3, utilizing the 3, and going in the 5th and 6th, and you're utilizing the next one, those right there are free energy range, ether, free energy. There's no closed circuit loop. Like electromagnetic permanent magnets are a closed loop. Now, what we did here is we have a closed loop of magnets. So when I turn this power off, and that is no longer electromagnet, okay, it's still a closed loop now. So we're going to be oscillating. We're going to be flipping the poles in all these magnets. So these magnets are going to be a major part of what that pipe is reacting to the 2 glass, which will actually be 4, because we're remember we talked about getting it in your dipoles. So right here, we'll have 2 dipoles here. We're going to have well, actually, this will be 2 dipoles, because we'll have 1 capacitor here and 1 here. But when we add the other pipe, we'll be getting into the 3rd and 4th dipoles. So in 4th dimension. the third dimension of the dipole. And we're going to stretch out the dipole. And I believe this is where we're going to break into some new studies, especially because I love bismuth, okay? And I wrote here as a note that bismuth has always been a great conductor, and its angle or lattice of its makeup on its composition over here, which bismuth is right here, periodic table number 83. Okay, there's bismuth, and it's easy to melt, but it's off 30 degrees of magnets, so a magnet won't stick to it. But what we're going to experiment is we're going to try using it in vacuum when we get to the pipes running. We'll go down the road and talk about how I'm going to utilize it, but there's a reason we're going to use it, and that is that a magnet don't stick to it. But there's properties in it there that are unbelievable because of its angular position, of its lattice, of its atoms in itself when they're hardened up. You guys, peace out, my brothers. Leave your comments. Peace.